an original.
From Story Studio Network.
Hi, I'm Dean Gation, and this is the Powerful Connections Podcast. Welcome to Season 2. For many years, my efforts as a service provider were focused on developing, planning, and building high-voltage projects. Whether it is transmission lines, substations, distribution systems, or connecting generation, projects with my involvement have been successful. My company, DGG5 Advising, is the opportunity maker you need for your energy and construction projects. This season, my guests and I will focus on specific topics of interest and bring them to light in interesting discussions. On this episode of Powerful Connections, we're happy to have Carl Haeussler, Director of Business Development, Brookfield Renewables. We're going to discuss generation at a high level with a focus on battery energy storage systems, otherwise referred to as BESS. Please welcome to the show, Carl Haeussler.
Thanks, Dean. Pleasure to be on here today and looking forward to chatting with you for the next half hour or so.
Should be good. So, Carl, please introduce yourself to our listeners.
As you mentioned, I'm Director of Business Development with Brookfield Renewable. Right now, I'm overseeing large-scale utility BESS installations in Eastern Canada, primarily 3 sites in the Ottawa area. Been in the industry for over 15 years, overseeing about 2,500 megawatts of greenfield energy developments, ranging from wind, solar, hydro, natural gas, and now BESS. So it's been an exciting time. I've worked in both worlds as a developer and EPC contractor on some of Canada's largest flagship renewable energy projects. So really pleased to be speaking about BESS and the technology and how it's developed and power generation as a whole.
Thanks for joining me today. Tell us a little bit about Brookfield Renewables and EVOLUGEN.
So Brookfield's a large Canadian company. We've been around for well over 100 years. It's a large-scale asset management company operating in renewables, real estate, and infrastructure. They also sometimes act as an equity partner or a silent lender for large-scale developments. We own many development companies, more referred to as portico companies, globally, ranging from Canada and the U.S. to India, China, Spain, and in England. So we're pretty well diversified. We currently have a large multi-billion-dollar objective over the next few years to develop BESS and other renewable sites largely in North America, but also across the globe. So it's been a great experience this far working with the Brookfield team. The company is well poised with strong leadership like Bruce Flatt, Connor Teskey, and former board member Mark Carney. I couldn't be more excited. You've
been involved in numerous positions of project development, project planning, and project management. And congratulations on your latest appointment to Brookfield. We enjoy Ottawa and Gatineau area. It's a favorite of ours. But Carl, we want to highlight today how BESS has had a dramatic cost reduction and technical evolution in recent years. The main goal is to support the operation of power grids. Even if there is a deep penetration by hydroelectric, solar, and wind in grid systems, this is still a great solution. So tell our listeners about the beauty of battery energy storage systems.
Yeah, for sure. You nailed it there, Dean. BESS is truly fascinating technology, and it's seen extreme growth. Right now we were looking at a 5 megawatt hour container solution, and within the time we've been looking at it, they've developed into a 6 megawatt hour. So the growth is truly staggering, similar to what we'd seen in the wind and solar industries. The technology itself is generally pretty boring at site. It's a 20-foot sea container. You'll have 1 to 200 of them on site for a mass utility scale installation. But the concept seems simple. In reality, it's pretty complex. It's truly a technological feat. They're interconnected, into large utility scale grid connections to, household installations at 120, 240 volts AC. The general concept is they can be utilized during peak times to offset costs and reduce peak demand by using a generation that's, produced through the night on some of our large bulk scale energy systems, which may produce cost-effective energy. So on top of peak capacity reserve, the BESS systems are more complex than how they visually perceived. Being a stationary storage device, they provide voltage regulation, frequency droop compensation, as well as have the functionality to black start grids during mass scale outages.
It's a lot of versatility. And in looking at Ontario's electricity sector, it's seeing a huge demand and growth. So there's a need for a mix of generation supply to deliver the want for grid decarbonization. So this has pushed the IESO to acquire huge amounts of generation on a large scale. The IESO has been working on their long-term plans to find and allocate resources to meet the demand and the needs of the future of Ontario. So give us an idea of the best projects that are built and will be built. And I guess more specifically, what's the range of the size of them in megawatts? What is kind of the footprint they encompass, and what voltages do these connect at?
This is a great question, Dean. BESS systems are very diverse. They're wide range in size, from 500 kilowatts from residential installations to 400 megawatt large utility installations in the province of Ontario. They typically have a 2 to 4 hour duration capability, which means, the batteries will discharge to the grid or load demand for 2 to 4 hours and take a little more than that to charge. They have a little bit of an energy loss in charging. The footprints, like the nameplate capacities, vary greatly in size. They can be a small wall-mounted installation on the wall of your house to up to about 18 acres for the largest installations in the province. For utility scale installations, you could squeeze between 80 to 100 megawatt hours of BESS into 1 acre. To put that into perspective, 1 megawatt on the LT1 projects in Ontario can service about 1,200 homes for up to 4 hours. In comparison, an average size gas plant that's 200 megawatts would require at least 20 to 30 acres of land for development. So quite substantial reduce in optimization in usable area. Mm-hmm. Grid voltages that they can be connected to are literally from 122 volt, 240 volts, as I mentioned before, up to 500 kV Hydro One utility grid connected. Very wide band of utility connections. Typical utility scale installations operate at 35 kV at the feeder level and operate at 600 volts AC or DC coming out of the DC battery container.
Quite versatile. So let's get into the economics of these BESS facilities. They're very cost effective, but what drives that?
So this is a big question. Do these BESS installations make economic sense? We'll take a brief step back. The concept of BESS is to store excess energy from the grid and dispatch it in time of need, typically between 7 a.m. and 7 p.m. for the highest load demand of qualifying hours in Ontario. Currently, the province is producing energy in excess due to our base load nuclear power energy, and in oftentimes mainly through the night, and thus we are selling the energy to our neighbors at a loss, the neighbors being Quebec and primarily the United States of America. This inherently taints the economics utilizing bulk energy sources such as nuclear in the province of Ontario, wind as well. Now, circling back to what advantages BESS truly do provide, instead of selling bulk cheap energy at a loss, primarily from, like I mentioned, nuclear and wind, BESS allows the grid to store that energy to be dispatched at a more preferable time, which changes the economics substantially for our province as a whole, right down to the time of use ratepayers. So what does that mean? If we're taking advantage of our bulk energy sources and selling it or using it when we need it, that means the time of use ratepayers are paying less for their energy. Like, I was on a forum and a panel with IESO in the city of Ottawa a couple months ago, and I asked them directly why they're choosing BESS as a primary bulk energy source to install on the grid, and their direct response was, right now it's the most cost-effective solution on the market, and they're using it to taper electricity rates and hopefully reduce them overall for the time of use ratepayers. To put into context, the latest procurement for natural gas plants saw prices clear at about $1,300 per megawatt plus, and BESS installations were substantially less at $1,000 per megawatt or less.
That's a big impact. That's a big statement for IESO to make, and it shows that they're observing what's going on and there are some good opportunities. So when people are thinking of batteries, they have an older established idea that it's chemicals. But the new lithium ion phosphate batteries are metals. So the safety and capacity and design makes these BESS systems very attractive to operators, but there are guides for installation of the BESS from NFPA. So I know the National Fire Protection Association, or NFPA, is the core information that is used to save lives and reduce loss that safety professionals around the world use. So I'm familiar with NFPA 70E, which is a standard for electrical safety in the workplace. Now, NFPA 855 is the standard for the installation of stationary energy storage systems. This is the guide on mitigating risks and the fire protection of storage systems. It's quite extensive. The latest version is 2023, so it's current. Talk about some of the controls in design and setup that BESS attracts from a safety standpoint.
This is certainly an important question, Dean. One of the most common questions I receive when speaking of BESS is my home going to burn down if I live close to one of these things? I assure you the fire hazards presented by BESS are very real. However, with the latest technology, codes, and standards, also very reasonably manageable and are no more risk to our everyday life than that of the lithium-ion cell phone batteries in our pockets that all of us carry around every day. In all reality, those are likely a higher fire risk than the latter. And that's common statistics seen within the fire services across Canada. NFPA has worked very hard on their latest revision to the NFPA 855 over the past quarter to accommodate the rapidly growing BESS technology. The major design considerations outside of rigorous real-time monitoring, sensing, and controls are the measures taken to manage the risk of fire and explosion. Those are the key ones. Three major things in mind are the key items being proposed to manage these risks. First, the designs of the latest BESS containers use NFPA 855 considerations to prevent propagation from one container to another in the event of a fire incident. The use of active and passive ventilation mechanisms, insulation, and container design as a whole reduce the likelihood of one of these containers spreading fire without adverse external factors basically being zero. They validate their performance of their system designs by conducting a burn test, which is generally just a test where they light one of these containers on fire and they place it next to an adjacent container and let it burn to the ground to see if it propagates from one to another. Generally, it takes them a few hours to get the thing lit on fire, usually about 4 to 5 hours, and they burn it up to temperatures from 600 to 700 degrees Celsius, and they let it go and see how it goes, monitor the toxicity of the smoke, monitor any potential soil contamination, etc. They found with a lot of these tier one suppliers that the fires do not propagate from one container to another on their own.
That's good.
So it's proven that the design considerations that have been made in the containers are generally robust and operate as they should. The second and the third measures are, as I'd mentioned previously, are active and passive ventilation mechanisms for explosion prevention. The latest version of NFPA 855 calls out a new standard, NFPA 69, where active ventilation is used to release off-gassing and pressure within the container during an overheating event. The active ventilation is just a louver with a fan. When they sense high pressure and off-gassing, the louver opens and the fan sucks out the gas, relieving the pressure in the container. The passive ventilation is a previous NFPA standard 68, which calls for deflagration panels to be installed on the container, which are a mechanical pressure relief door that opens in the event of certain pressure is achieved within the container. When the door is open, the pressure and off gases are released from the containers without any electrical powering or input. So it's really at this point with the new standard, it's become a mechanical redundancy in the event of an auxiliary failure.
Yeah, and in a lot of the safety standards have always had such levels of protection, multitudes of safety, multiple levels of things. So these systems are extremely safe and very good operation, and they monitor themselves very well. So there is a widespread deployment of BESS around the world. They are more prevalent in grid systems like Ontario, where there is the mix of nuclear, hydroelectric, wind, and solar. New opportunities and markets are evolving for BESS. So talk about a couple of those things. First, kind of the importance of BESS, and then second, the stability BESS brings to grid systems.
Yeah, absolutely. The value of BESS is revolutionary. It's not optional for Ontario. IESO predicts energy demand in Ontario to grow by 75% by 2050. So there's simply no other technologies available on the market that are financially feasible enough and have as low of an impact to the public as BESS to support that type of growth. The large nuclear and hydro plants, they might take decades. Natural gas and wind, the sheer footprints are so large that it's a significant impact and undertaking with the public. Wind may be a cheap energy source, but its intermittency poses a serious challenge in achieving these energy demand targets. Natural gas is great for addressing peak demand, but are not feasible for Ontario ratepayers to pay the premium to use natural gas in a market where our electricity rates have skyrocketed over the past few years. I mean, you and I know I see the electricity bill come in, and sometimes I'm shocked, right? So I think it's the best option on the market to, for one, manage our ratepayers' cost, and two, promote the growth needed to bolster our businesses and residential development. Without adding excessive amounts of new infrastructure will be required to build new power plants. So instead of building a power plant and a T-line and it's going to service from Toronto to Ottawa, they're putting the BESS right on the transmission grid right away where it's ideally located without building out new T-lines. From a grid stability standpoint, it's one of the best solutions. It's an AC to DC conversion system, so they are very dynamic. The inverters themselves required to support the BESS sites add great reactive power flexibility, voltage and frequency droop regulation. They also have the capability to provide black start and grid forming services, as I mentioned earlier, in their event they are needed to due to long and unexpected duration outages.
Mm-hmm.
BESS adds system stability similar to a water tower on the water system in a municipality, if you want to think of it like that. The BESS acts as a water reservoir, which ensures water is stored and provided to our households adequately at a constant and strong pressure. So imagine, if every time you turned on the water in your house, it was just sputtering water versus pouring out at the rate you need to wash your clothes and your dishes, is a pretty direct comparison.
Maintaining pressure on stuff or maintaining ability for power, it's the standby process that we've got in place, and we're very lucky that we have it. So the next item I was curious about, there's a number of good BESS manufacturers that provide solutions to developers for Brookfield Renewable. Tell our listeners about the entire asset that you need to develop, design, and build for the complete BESS system to connect it to a utility or the provincial grid.
There's a lot to unpack on this question, Dean. I'll try to keep it simple. The project development life cycle starts with deliverability studies released by the IESO, where they've mapped the transmission system and distribution system out on nodes so they can assess where the energy is needed the most. There first simply needs to be a demand, similarly like IESO had established regarding the project growth and energy demand in Ontario. Strategic locations are spotted within the province based on the needs to deliver energy. So we site these facilities exactly where they're needed. From there, we begin preliminary engineering. We lay out the site. We understand cable sizing, how many containers are needed to meet the IESO requirements. From there, we establish a project footprint and begin to do impact assessment studies for the environment, the public, the traffic, the workforce, the whole 9 yards. And we kind of vet that through our permit applications, which includes environmental permitting, municipal permitting, IESO system impact assessments, and Hydro One customer impact assessments. From there, we kick off with our major procurement. So we take a look at procuring the major equipment such as the BESS itself and the high voltage equipment, which may have long lead delivery times. Once that's underway, we go through the whole contracting stage and we host competitive RFPs with key proponents who are EPC contractors who can design, build the facility and take it into service. Once we get through all these things awarded for the equipment supply agreements for the BESS, for the EPC contractor, we have our ancillary permits from the environmental agencies, the city, and all other parties. We are basically ready for site mobilization and construction. So obviously that starts with the land preparation, clearing trees, grubbing, and then we go through to the actual concrete pours, the site grading. Sometimes we use helical piles for the foundations. We receive the containers. Usually they deliver the containers at about 8 to 10 containers per day. Install those, and at that point we get ready with some auxiliary services and provide energy for cold commissioning, where they check all the statuses, they check all the alarms, the control points, they make sure the air cooling and heating system is functioning properly. Once that gets going and we have our substation and T-line interconnected and we have backfeed, that's when we generally start hot commissioning. And hot commissioning is where we're going through the works, making sure the inverters are programmed properly, the ramp rates up and down are proper, and everything's functioning as it should. Once we get through that whole hot commissioning process, and it's usually broken down by feeder. So if you have 5 feeders on a project, you go through 1, 2, 3, 4, 5. That's where it gets us to our performance testing. Performance testing is just to show that we can deliver the nameplate capacity of our site over the duration capability, which for LT1 procurement was 4 hours. And once we've achieved that, we hit COD, our commercial operations, and the facility is formally into service. It takes about 4 to 5 months to go through cold commissioning, through hot commissioning, and performance testing. And it takes about 8 to 10 months to get the site ready for construction. So it's a pretty timely development. Things rapidly evolved. The hydro plants I built in the past, is a 2 to 3 year development at least. And the construction could take a significant amount of time. So, talking a pretty fast-paced work environment to get this thing into service, which has benefits for the ISO grid in general to get these projects online early. The full life cycle of these developments is usually anywhere between 2 and 2.5 years. Could be a little longer depending if the projects require zoning bylaw or some other particular permitting requirements. But yeah, about 2 to 2.5 years from inception of development to commercial operations.
the big thing inside of all these big projects, people forget about just the pre-development to get a concept of, and we've talked about it many, many times, the politics and economics to work, and then the actual schedule and financing and everything, so there's a lot of things that happen even before you even think about looking at land and EAs and everything else. So these construction projects with this design are substantially reduced, and the impact is felt pretty quickly. You get a generation project up and running in 2 or 3 years. That's pretty impressive.
It is, and the current supply chain come to the task. They have a pretty quick lead time, and the containers are in great supply. So there's a lot of tier 1 vendors who can deliver the rates we need to achieve these projects. Mm-hmm. They have a good time frame, and the IESO needs it for the province of Ontario.
Absolutely. Well, this was a great discussion. I'm glad I asked you for your insight on BESS. It's neat that to see you doing what you're doing, and I think Brookfield's got a good person in place, and I want to thank you for being on Powerful Connections and continued success at Brookfield. But before we close this episode, please provide a few closing remarks for our listeners to ponder on.
I appreciate you having me here today, Dean. It's been great. It's always a pleasure speaking with you. The need for energy in the province of Ontario is greater than it's ever been. BESS is necessary to facilitate the growth objectives set forth by the province. Business, residential developments, and other infrastructure projects require these BESS developments in order to keep up with the modern day demands. We're talking about data centers. We're talking about large residential growth, commercial businesses that need the energy to thrive. And it's not just at a small scale. A data center needs at least 100 megawatts of energy. And we're just right now, the province isn't poised to deliver that amount of energy. So it's rapidly evolving and at a higher demand than we've ever seen. The other part of this is right now, Ontario operates the cleanest energy grid in North America, similarly to California, if not even in the world. Mm-hmm. And we have a lot of wind and solar assets that greatly benefit from having this type of installation. Nuclear energy that we sell off at pennies for the dollar also benefit hugely to manage our electricity rates for the time of use ratepayers. So across the board in the province, it's a win-win. I see that these installations provide the robust grid connection points that the IESO needs, and it also allows the ratepayers to manage their costs a little better when it comes to paying the bill at the end of the month each month for our electricity bill. Looking back about 10 or 15 years ago, when we started first learning about these renewable energy developments, it was a future thought, it was a concept, but now the future's here with all these BESS and wind and solar installations, and it's never been a more exciting time to be in the industry. So thank you again, Dean, for having me.
Thanks very much. Appreciate your insight and thought leadership today. This was a great episode of Powerful Connections. In this episode, we discussed the impact and benefits of battery energy storage systems with Carl Haeussler from Brookfield Renewable. Rainey, what are your thoughts on my discussion with Carl?
It was a great conversation with Carl Haeussler on battery energy storage systems. He had lots to say in a short amount of time. BESS has come from mostly a concept a couple of decades ago to rapidly changing technology that's become a mainstream part of electricity generation systems. From what Carl said, typical parts are the size of a 20-foot sea container, and the installations can be one battery or up to 200 batteries that are connected together. So when you look at this, they can be as small as 500 kilowatts connected at household voltage, which is 120 to 240 volts, up to very large-scale utility-size systems of 400 megawatts with connections to the 500 kV transmission system. Very, very versatile. They can charge through the night when there's cheaper excess power, and then they can discharge through the day to lower the peak demand from more expensive generators, which brings the price of electricity down. They also provide stability on the grid operation, and they can help restart other generations, like a mass-scale outage that we've suffered in Ontario before. The footprint is small. A BESS of about 80 to 100 megawatts can fit on 1 acre, whereas a typical gas generation plant of 200 megawatts requires 20 to 30 acres of land. Cost to generate is typically $1,000 per megawatt for BESS versus around $1,300 per megawatt for gas generators. Now, today's technology is lithium-ion batteries, and they're tested to a high level of standard to ensure that they're very safe. BESS installations are easily placed where the load demand is, so it's without the need to build new transmission line. Their concept to connection time is much shorter than conventional generation. Carl's discussion illustrated for us the future is bright for BESS installations to become a standard part of the electricity grid system in Ontario. They'll help reduce electricity rates, reduce emissions, make use of excess power from renewable and non-renewable sources, and they'll help stabilize grid systems as load capacity comes on or drops off the system. We used to use coal plants for that. And they take up much less land than wind, solar, gas, or nuclear generation. They are a necessary piece to the puzzle for the electrification future in Ontario. What are your key takeaways, Dean?
Battery energy storage systems are good as a peak time capacity reserve, but are more complex than perceived. They provide voltage regulation, frequency droop compensation, and help to block start grids in times of major outages. BESS operates at different voltage levels, so as we found out, it can be connected at 500 kV or 230 kV grid voltages, as well as utility scale installations from 34.5 kV to as low as 600 volts. So find the right solution and design for your needs. The value of BESS is revolutionary and is not optional in Ontario. The IESO predicts energy demand in Ontario to grow by 75% by 2050. So the need for BESS as part of the energy solution will be there. From a grid stability standpoint, it is one of the best solutions, so find the opportunity to bring this solution to your system, customer, or project. Look forward to hearing from you after you listen to each episode. I encourage you to subscribe to Powerful Connections wherever you get your podcasts. Share the podcast with those you feel will find it interesting and useful. Connect with me on my website at dgg5advising.com or find me on LinkedIn at Dean G. Gation.
This is SSN.
Story Studio Network.